Okay, I think so. Paolo Saracco about globalization for geometric partial comodules, and then he will be happy to answer your questions and comments. Okay.
Hello, I'm Paolo Saracco from the ULB of Brussels, and I would like to present to you our most recent achievements concerning the globalization question for geometric partial comodules. But before doing this, please let me thank you for watching this video, and let me thank the organizers for giving me the opportunity of presenting my research here today. Now, our main motivation for studying geometric partial comodules is because they provide a nice unifying categorical setting where to deal with the very vast panorama of partial structures that we have nowadays. And since this globalization question is one of the most relevant questions in the field, it seemed natural to us to address it from the point of view of geometric partial comodules. But before going into the details of the theory, let me give you a very quick historical and motivational introduction to the topic. So partial structures appeared for the first time in the form of partial actions of groups on sister algebras and sets, which can be interpreted as actions of groups by partial bijections instead of global ones. And already since the very beginning, an important role has been played by the globalization, which states essentially that any partial action of a group is in particular the restriction of a global action to a not necessarily stable subset. Now, in the meanwhile, the theory evolved quite quickly, so partial actions of monoids and topological monoids and their globalization has been introduced, and also the theory entered the realm of algebras with the introduction of partial module algebras, partial comodule algebras and their globalization, and so on and so forth. So concretely, over the last 25 years, we really experienced a proliferation of partial structures all around mathematics. So it arose the need to having a unifying approach to partial structures, and in particular to their globalization. And this unifying approach has been offered by geometric partial comodules, which enjoy the great flexibility of being defined over an arbitrary coalgebra in a monoidal category with pushouts, and they are objects together with a partially defined coaction, which is required to be co-unital in the partial sense, of course, and co-associative in the partial sense as well. Now we can also consider morphisms of geometric partial comodules, so in fact we can consider the category of geometric partial comodules over a certain coalgebra. Now, the easiest example of geometric partial comodules is provided by global comodules. So the theory of geometric partial comodules encompasses the classical theory of global comodules over coalgebras in monoidal categories, but thanks to their flexibility, we can also recover many of the known partial structures as examples of geometric partial comodules. This is the case, for example, of partial actions of groups or topological groups on sets or topological spaces by considering the opposites of the category of sets and of topological spaces. Also, partial comodules and modules over Hopf algebras are examples by considering the category of vector spaces or its opposite respectively. Even partial comodule algebras are geometric partial comodules in the category of algebras, and partial Hopf comodules over a bialgebra are geometric partial comodules in the monoidal category of modules over the given bialgebra, and so on and so forth. There are many examples that can be recovered as particular cases of geometric partial comodules by suitably choosing the underlying category. Now, in this more general categorical setting, the globalization of a geometric partial comodule X is defined to be a global comodule Y together with a morphism from Y to X in the underlying category, such that the original geometric partial comodule structure on X is induced by the global comodule structure on Y via this morphism P, in the sense that this square is a push-out square in the underlying category. And furthermore, we also want Y to be universal in the sense of being terminal among all the global comodules admitting a morphism of geometric partial comodules to X. And now we want to restrict our attention to the full subcategory of those geometric partial comodules which are globalizable. And in this case, the question becomes, when are geometric partial comodules globalizable? Or better, how can we describe this category of globalizable geometric partial comodules? And the answer is provided by our globalization theorem, which states exactly that a geometric partial comodule is globalizable if and only if a certain equalizer exists in the category of global comodules, which is providing the candidate globalization, and if the original geometric partial comodule structure on X is induced by the global comodule structure on this equalizer in a natural way, in the sense that this diagram is a push-out diagram in the underlying category. Of course, if these necessary and sufficient conditions are satisfied, then the equalizer becomes the globalization of our geometric partial comodule. And in fact, if we restrict our attention to the full subcategory of globalizable geometric partial comodules, then this globalization construction becomes functorial in the sense that it provides a right adjoint to the fully faithful embedding functor from the category of global comodules into the subcategory of globalizable geometric partial comodules. But now let us apply our globalization theorem to some of the cases I was mentioning before. For instance, if we apply it to partial actions of groups or monoids, then we recover the well-known globalization theorem for these due to Abadi and Kellen-Clausen. The same for topological partial actions of topological groups on topological spaces. For the case of partial comodular algebras, we find an essentially new globalization for these, thanks to the concrete construction of our globalization theorem. And since the globalization theorem provides necessary and sufficient conditions, we are also able to identify obstructions to the existence of a general globalization theorem. That's what's happening, for example, in the opposite of the category of topological spaces, or in the categories of algebras and of commutative algebras. In these cases, we know that not every geometric partial comodule is globalizable. But probably the most important application of our globalization theorem is the globalization for geometric partial comodules in abelian monoidal categories. In this setting, what we proved is that if we are working with a coalgebra which is nice enough, in the sense that its category of comodules admits all equalizers, and these are preserved by the underlying functor to the base category, then in this case, all the geometric partial comodules are globalizable, and we can concretely compute their globalization. So, for instance, in this way, we have a globalization for partial modules over Hopf algebras, and we also proved that it coincides with their standard dilation when considered as partial representations. We recovered the globalization for partial representations of finite groups. We provided a completely new globalization result for partial comodules over Hopf algebras, which was not considered before, and also for partial Hopf comodules over bialgebras, which, by the way, allowed us to prove a structure theorem for these, which closely resembled the classical structure theorem for Hopf modules proved by Larsson and Zwitter. But this was the most important result I wanted to call your attention on, and with this I conclude. I thank you very much again, and I warmly invite you to read more on this topic on our recent preprints. Thanks again.
Thanks, Paolo. So once again, I'm asking to the people here and online if there is anyone who would like to ask a question. Please comment. Sorry.
Don't worry. First of all, thank you very much again for this opportunity. I beg the pardon of those who already heard this talk at least once or twice. I tried to make it a little bit different. I hope I managed to. There's just one small comment, because at a certain point I suspect somebody thought I was cheating, because I said that topological partial actions are globalizable, and then I said that a globalization theorem does not exist in the opposite of the category of topological spaces. The point is that topological partial action is a particular kind of geometric partial commodule. So it's still true that not every geometric partial commodule is globalizable, but topological partial actions of groups are globalizable. And the same is happening, for instance, in the category of commutative algebras and algebras. Our obstruction theorem is saying that some pathological cases are not globalizable, but all the cases of interest that has been considered in the literature up to now can be recovered by the globalization theorem I presented here. If there is any question, I would be very glad to answer. If not, I would be very glad to go back on the other room.
Sorry. Yes, so now, are there any questions, Paolo? Or comments? I don't see any. So I think we can thank Paolo again